Earlier this summer, we had an afternoon chat with Professor Valerio Lucarini. He holds the chair of Statistical Mechanics at the University of Reading, and he's occupied with a wide range of research areas, from probability theory to climate dynamics and chaos theory. In the field of climate science, he is known for his extensive work on devising a new theoretical framework that would explain the present and the past climate states of our planet. Especially the melancholia state is one that has been inspired by Lars von Trier's movie. He has received numerous awards from the London Mathematical Society and the European Geophysical Union, as well as the Russian Academy of Sciences. Last summer, he shared with us what led him in his path, as well as his views on the role of the scientist in modern society. For those in a rush, you can skip over, otherwise enjoy the rest of the podcast. I am Athanasia Nikolaou, and this is the LeWiBo podcast series.
Okay, so I'm happy here to present Professor Valerio Lucarini. He's a professor of statistical mechanics in the University of Reading in UK. And he also was awarded the Richardson Medal from the European Geosciences Union recently for his work in climate and mathematics, but he's going to tell us more about it himself. So let me welcome you first.
Thank you very much, Nasia, and it's a great pleasure to be with you guys today.
Thanks for finding time. So the first question I want to make to you is, let's take it from the physicist. So the traditional image that people have for the physicist, people think always of someone who is deep into the books, preferably using also the pop culture reference to Einstein. So the hair have to be in a specific way. It's mostly men. So was this stereotype true when you actually started to study physics?
Well, let's say that surely it's, at least in my case, it was choosing my path in physics was something that was extremely important for me. It's something I've been thinking about since I was very young. And to me, it was something between a call and a huge passion of mine. And let's say the idea of studying physics was extremely important for me to develop, at least as a guy, a teenager, a young adult, my way to look at the world. So I can say that for me it was a full immersion, and it was something I dedicated myself very, very much to. I'd say the stereotype, I think the stereotype with time, I mean, of course the stereotypes are extremely pervasive. As a scientist is some strange human being in the usual, most commonly in social contexts. So it's hard to associate, to make a sense of why one can choose to study science. And obviously the Einstein imager stereotype is extremely powerful and, of course, extremely wrong, and just captures something, I would say, extremely shallow and of what can be the motivations of a scientist. Of course, you find any kind of human being doing scientist. I had to say that, of course, there is some sort of attitude many people develop, maybe including myself, to try to fit a bit with the stereotype. And it's something that, I mean, I wouldn't call it healthy or unhealthy. I tend to refuse these categories. But let's put it this way. I would say that there are, in my career, among the most talented or the most, interesting guys I've been studying and working with, of course, there is an element whereby doing science it's a job, it's something you study, but it's also often a great passion of yours, something that is extremely important. So sometimes this passion can become overwhelming. So I, as an example, as a student, I have to say I have spent many long evenings and nights studying for the pleasure of it, getting a sort of an intimate relationship with what was the topic of my study and was my intellectual passion, and I don't regret a minute of that.
That's great. Actually, that's another thing I wanted to ask you next. Like you described, you have a passion for physics. So how did you choose to become a physicist among so many other things? For example, engineering or mathematics could also be using similar studies, right?
Well, when I was very young, I realized in a way, I will not go into the details because it's something that I find extremely personal, but let's put it in a sort of in a coarse-grained description. I realized at a certain point that science was giving me some sort of powers to understand things that other people couldn't understand. So it was endowing me with abilities and skills to look at the world in a different way. About what to study, my scientific passions were diverse. And as of today, if someone asks me who are my scientific heroes, so one of my scientific heroes was and is Charles Darwin, an example of ability to understand complexity and to be able to transform a fixed vision of the world into an evolving vision of the world. And so this, I think, is an intellectual effort in the history of mankind. Mm-hmm. And another one is Lev Landau. I also admired, so that's something I want to say. I never just admire the skill. There are many, many incredibly skilled scientists. But I always appreciated a lot the men behind the scientists and the ability of the men to relate, to be an intellectual somehow. Mm-hmm. So, as an example, Charles Darwin's scientific investigation were motivated by his deep political thought against slavery and against racism. So, science was a way to overcome a lot of ideas, a lot of sort of common and tragic ideas that were around him, as a member of a very privileged class that he was. In the case of physics, of course, the first and greatest example is, of course, for me, Galileo. And I remember very distinctively the first time I visited Pisa and I saw where Galileo was born, and the effort of this man to somehow really change the world in a way that it's art. I mean, we can't even imagine a world before Galileo in some sense. Okay, we live in another era. The physics was able to somehow look at the natural world was essential. I didn't want to live in a world of pure logic. I wanted to live in a world that had senses, that had feelings, and that had colors. And that, of course, on the other side, certain degree of universality. So I wanted something that allowed a theoretical approach and a theoretical, more, I would say, universal / systematic look, which other disciplines that I love a lot, like biology, at least in my perception, didn't have. Mm-hmm. And but engineering was never my thing, because using the words of somehow the difference is that I am extremely not curious about devices. Mm-hmm. And my way of thinking is, I would say, extremely far from the idea of solving problems. I'm really not good at. So I'm not good at being able to solve a problem in a general sense. Like as a student, I surprisingly had a lot of, relatively, but troubles in doing exercises. It was not my thing, okay? I mean, I'm talking relatively. It was a very...
of course, I can understand, because one looking at your CV can see that there is, of course, some, good quality to what you were doing. So, of course, you were doing something correctly.
To me, it was, and I mean, I'm blushing in saying this because it sounds, and it is, of course, very arrogant. My goal was and is somehow to develop some sort of vision on the world. And on aspects of the world that I feel I can relate to.
That's why you concentrated more on theory in your track as well, right? You chose the theory.
Yeah, I don't know. I mean, the theory can be also extremely instead oriented towards addressing specific issues. I was first extremely poor as experimentalist. I was not. I just didn't have the talent and maybe not the interest. I mean, I think actually talent is a wrong word to use in general. To me, what motivated me was not doing something difficult or things that no one has ever done before. So in that sense, I'm not so keen on scientific discovery. I was and I am more keen in developing a broad understanding and a comprehensive understanding of a large class of phenomena. And of course, then dedicate myself to better framing the gaps and the holes. So that's somehow what motivates me more.
Thank you. That's actually, you touched upon a lot of things. I want to stay also since now you talked about the experiments and the theory, was there any particular professor that you remember made a big impact with you? Or this was not the case at any point?
Of course, there was. I mean, I studied in the University of Pisa and Scuola Normale, and in that system you have some sort of a mentor that then becomes your supervisor since quite early age. So already in my third year, I started to become some sort of scientifically active, so to say, try to develop my own things. And my mentor and supervisor was Franco Bassani. He was a great, a truly great Italian physicist who is one of the first one who introduced condensate matter physics to Italy. That was my first area of work. And he was very much of an intellectual type, and the person who tried to, talk many different languages, both in science and outside science, and somehow encouraged me a lot also to avoid becoming a sort of a one-dimensional being, which was extremely was tempting in the context where I was being very successful at early age. So instead, you sometimes you should not just focus on science. There is much more. Apart from life, but even intellectually, there is so much more. You should devote and dedicate time and efforts to, also to improve your abilities as a scientist. And I have to say that with time, I realized how important it was to broaden my views, and how this has allowed me later in my career to achieve results that I would have never been able to. I would have never been able to, I believe, to reach otherwise.
Yeah, so that's a good point. It fits one of the questions I had further. So, what is the field you can say was further away from physics that you ever tried to look into? Not necessarily for research, but for your own.
Sure. No, I was for a long time. I was an extremely militant political activist, and this has been for many years. Was for many years a big part of my life, and I was participating groups and association, and shortly also the activities of some parties. And to me, it was essential to avoid ending up in the tourist Eburnea, in the ivory tower where science sometimes puts you. And that I found an extremely claustrophobic word. Whereas many friends or colleagues of mine clearly did love being in this sort of small, controlled universe of few people who have all the same priorities, I was very happy to immerse myself in the wider world and to explore it. And on the other side, to me, doing science was a political act of freedom in particular. So I saw science, culture in general, but science especially, was a formidable way to develop my own spaces of freedom and try to encourage others to develop theirs.
Okay, I'm going to read you here one excerpt from the editorial of the Nature Springer from this month. It's 5th of June 2020. It quotes, "A call to arms to all physicists. With your mathematical training, you are in a strong position to understand the basics of how epidemiological modeling works. And for your non-scientist friends and family, you are an accessible and credible source of information. So next time you call your dad, explain the background to the media stories about models that he doesn't understand.
Mm-hmm.
So this fits well to the point you made before for Darwin, that he was not excluded from the society. And what is your take on the role of physicists for the society? So that's actually based on this, because this is referring to the recent case of COVID, of course, of COVID-19.
Yes, I think this is, you're asking a very important question. And I think here a discussion on science and methods and science are extremely relevant. So the problem is the image that the average person has of a scientist, and especially of a physicist, and this is partly also the image that at least a big part or an important part of the community of physicists want to give to the world, is the image of some sort of wizard who knows the truth and who aims for the truth. So when the person, the emphasis to the study of the fundamental properties of the matter, to the ultimate destiny of the universe. And this is seen as true physics and true science. So I personally refute the centrality of this. I radically refute the centrality of these scientific endeavors. Not that I think they are not relevant, but I don't think they are necessarily the most relevant. And as far as I'm concerned, I believe that the frontier of science is in the understanding of the many phenomena of non-equilibrium and of the irreversibility that we see around us, that for which we are just starting to scratch the surface, and we are just starting to develop a scientific method. So the problem is the moment you talk about complexity and understanding of complex phenomena, uncertainty becomes an essential part. So many people were sort of surprised that so much uncertainty exists regarding the spread of COVID-19, or in fact of any other disease. Because the idea is that if it's science, the scientists should know with arbitrary precision what's going to happen. So I think it's a duty. The first duty is to explain that science is an enterprise of uncertainty. It's not about truth. It's about reducing desperately uncertainty and making a sense of the phenomena around us. So I think this is, somehow it's a miracle that we are able to predict anything at all. So, that's the expectation that we can predict things with arbitrary precision, as if we have a crystal ball. It's just ill-posed. And it's partly the fault of the scientists themselves. And in that sense, some of the sentences attributed, probably not even truthfully, in fact, to Einstein, I want to read the mind of God, or stuff like, do not really serve a good, they're not really useful. And if Einstein said that, well, he said something very stupid, and indeed, it's nothing surprising. I mean, even absolute masters and genius can do that.
So we can't put the scientists under scrutiny for what they say. It is allowed. That's what you say.
Yeah, of course it is. The problem is that we should the great let's say the great step or leap forward we should do is to be able to communicate uncertainty. So we should be able to make clear that uncertainty is a part of any scientific statement of any sort. And that would change enormously let's say, the way science and scientists are seen by the society, and would really contribute to the common good. And say in the case of the area of science that now I'm mostly working on, that is weather and climate. So I have seen that in different cultures in different regions in the world, there are enormous. There is an enormous gap in the ability of the average person to relate to the concept of uncertainty. So, if you give if you provide the same information, like today there is 60% probability of rain, some people might easily understand what this means. Other people would find it absurd. And I'm talking about people with the average or even high level of culture and even of scientific knowledge. So some people would understand the statement as, I have no idea what's going on, which is not the case, of course.
Mm-hmm. Actually, that's good to talk about it. Do you think that this concept is, as you said, difficult even for people who are adults to understand properly?
Yes.
Do you think this is a gap that should be addressed already from school years or like from the curriculum, and especially the climate change one, because we want to move also to your topic?
Yes, this I think is, as I said, this is, so what would be, let's put it this way. I think that there is often a lack of understanding of, sort of representation of the goals and methods and challenges of science in the school curricula. But the most important thing is, improving this understanding and improving the greatest challenge to improve the quality of the information is to make clear that uncertainty is an intrinsic part of any scientific endeavor and of the understanding of any scientific phenomena. So this should come, because somehow the idea is you have to be able to interpret the information you're given and understand the level of confidence this information reflects. So as an example, if you read the weather forecast and it says there is 90% probability of rain, and then it does not rain, you shouldn't be too surprised. It's just 1 in 10 probability, which is, something, probability of 10% is something you face continuously.
Yes. Especially in the context of climate, though.
Yes.
Especially in the context of climate, you actually have to deal with this uncertainty unfolding in decades of years, right? So not even in the same day that you can evaluate, but you have to do it in decades of years. So that's one more thing that we can discuss, because you have done a lot of work on this. Mm-hmm. And one of the things that you see in the news, for example, a lot of times, is that whenever there is an extreme weather event occurring, they are frequently reported as proof of climate change. But let's start easily. What do we know today that we didn't know 20 years ago about climate change? What can we say with confidence? In the level of confidence that we have.
Oh yes, let's put it this way, that for sure in the last 20 years, there's been many improvements in our ability to understand the climate and to model the climate. And there is, the first thing is that we have, let's say, a much higher degree of confidence on the fact not only that we are observing change in the climate, but also on the fact that such a change is due to mainly to anthropogenic sources. So that's the first thing. It's not that we didn't know this 20 years ago, but the confidence on these statements has enormously increased. And slowly with time, the confidence is increasing on, let's say, climate change at smaller spatial scales. So the problem is our ability to detect and understand climate change is different if we consider different spatial and temporal scales. This has to do with the fact that we are talking about a complex system where the signal to noise ratio depends on the temporal and spatial scales we are interested in. Now, there are many aspects of climate that are still not well understood and that provide nowadays the sort of frontier of climate research, of course. So as talking about something that's dear to me, even if I've not worked much on that, is the fate of the Indian monsoon in the context of climate change, because you have contrasting effects due to climate change at large, so increasing the CO2 concentration, greenhouse gases concentration, and local effects such as the emission of aerosols in the Indian subcontinent and in South Asia in general. So the first one leads to a strengthening of the monsoon, apparently. The second one leads to a weakening of the monsoon, and it's not clear which effect will dominate on which time scale and how the nature of the monsoon will change. And this is essential. So it's not just, as an example, a reduction in the intensity of the monsoon can be seen as a reduction in the overall precipitation. But it's not just the overall precipitation. It's also about the statistics of precipitation. So the prevalence or not of erratic, very intense rainfall versus long dry periods.
Yeah, it's a phenomenon that is large in spatial scale.
Yes, but yes, absolutely right. So the monsoon has scales of months and spatial scales of several thousand kilometers. On the other side, inside it, many other scales are relevant in time and in space. So the change in the statistical properties should not be seen only in terms of the change on the longest and largest scales, but also as a change in the statistical properties at intermediate or even very small scales. Those can be extremely relevant in terms of impacts, in fact, because nobody lives in the average precipitation or in the average location. So
it's an imaginary place. This is not.
It's like the average person. It's a terrible place to be usually. So anyway, this is another aspect we should definitely take into account. Now, another, of course, two aspects of great relevance, and two aspects over which the focus of the scientific community has become more and more important is on the understanding of the properties of extreme events and of tipping points. So,
will you explain maybe sorry to interrupt you, what is the tipping point for someone who hears first time?
Yeah, sure, of course, yes, I was going to do that. So tipping points are, let's say, radical qualitative changes in the properties of, in this case, of the Earth system when some perturbations are applied. So in some cases, the response of the system to applied perturbation is smooth, one says. So that means it's, let's say, it's proportional, or anyway, changes regularly in a regular fashion with the intensity of the applied forcing. In some other cases, can be abrupt. And so there is a fundamental change in the properties of the system. And usually, these tipping points are associated with the existence of multistability. That is, given a state of the rest of the climate, more than one possible realities can be realized for the system of interest. One of the most famous of such tipping points is, say, the Amazon forest. So as an example, it's not entirely clear. If you say if you do a deforestation of the Amazon forest, it's not clear whether in long time scales the forest will regrow or whether a savanna will regrow instead of the forest. This would imply that the system is multistable. And one understands that these are very delicate aspects of the climate system.
And what would you say to someone who listens to the news, like not necessarily with a scientific background, but as you said, important to understand climate change, where they hear that extreme weather events are reported as proof of climate change?
Sorry, yes. No, this is okay. That's the problem. It's there are different views on this, but I think it's can be very misleading to associate. Some colleagues might think differently, but I tend to believe that it can be very misleading to associate an individual event to climate change. So climate change has to do with changes in the statistical properties. So what one can typically say is whether a given observed event would have been made more likely in the presence of changing climate rather than in the presence of a reference climate. Mm-hmm. So I think you can't say whether a tropical storm is due to climate change. This, I think, it's a very ill-posed question. What you can say is whether a tropical storm of that class in that location is more likely in a reference climate than or not than in a changed climate. So in that sense, you have to consider a multiverse. So many realization of climate and see whether that event is more likely in one set of realization, those corresponding to a reference climate, rather than in another set of realization, those corresponding to the changed climate. So on the other side, it is a huge area of research, the one associated with the detection and attribution of extreme events, attribution of the extreme events to climate change. My vision on this is in some sense conservative, in the sense that I tend to be wary of attributing events to climate change. On the other side, there is an important political and economic implication to this, because of course the damages associated with climate change come, for the most part, from individual and specific extreme events. So if you want someone to pay for climate change, you should be able to tell that this extreme event has to do or not with climate change. The importance of extreme events in the context of climate change comes essentially from the fact that damages and impacts of climate change, in the sense that it's not the mean changing climate that is the one causing damages, except in some cases like sea level rise. It is the changes in the tails of the distribution, so in the change in the destructive events, that are more worrisome. Okay?
Yes, it's interesting what you say when you say tail of the distribution. Anyone who has seen a distribution can make this association on what you mean, like the parts which are less probable but still part of the solution.
Yes, yes.
Right? And from your description, for a kid or an adolescent who grows up today, it looks like they should get familiar with more statistics than, 20 years ago than what was.
Oh, yes, so sure. I mean, the challenges, understanding the climate and its changes require, I would say, require the use of a much more sophisticated statistical tools than is usually done nowadays. And this applies also for the scientific community itself. I think that sometimes very important and difficult questions of relevance for today's science and society are strangely approached with incredibly old-fashioned statistical tools, almost elementary ones. Whereas the research, the development of the frontier of probability and statistics has given us many more tools. And I'm talking in particular about ways to characterize, understand, and predict climate change, extreme events. This is one of the cases. I just want to give an example. So there is, an extremely well-established theory used in many areas of science and technology, extreme value theory, which provides a sort of, I would say, class of universalities and robust tools for practically study extreme events. Believe it or not, in the report of the Intergovernmental Panel for Climate Change dedicated to extreme events, there is barely mention of this. The reason is, this is not the standard approach most climate scientists take for studying extreme events. So, we have a hugely powerful theory, which is for some reason overlooked by climate scientists, whereas, as an example, it is used, on an everyday basis by hydrologists, which are, pretty closely related to climate science.
I see. So there is a lot of more tools we could take advantage of, even within the community. That's what you say. And
sure.
For some reason, we are not spreading it efficiently enough.
I think so. And the reason is somehow, let's put it this way, climate science at large provides, I would say, incredibly credible source of scientific, it's incredibly stimulating. There are so many open problems, fascinating problems, both practically and theoretically. On the other side, so it's something where one should try to, think out of the box as much as possible, adapt tools, invent new tools, and learn how to pose questions. Because often the most difficult and most interesting part, rather than answering a question, in a field like climate, is to pose the right questions. because there are often no clear, it's not a one-way process. You have to better understand the phenomenon, you have to be able to define it. Now, the problem is the study of climate is often dominated by technology, and let me rephrase. So somehow what determines the priority, more than being the, let's say, theoretical challenges or the practical issues, are the technological developments in terms of modeling and data processing and data collection and data storage. So somehow we are driven by the infrastructure rather than by the scientific question we really want to address. So this makes the progress a bit sluggish, and it tends to favor the research, the very incremental research that uses the existing framework and infrastructures rather than promoting innovative research. It's easier to go along the well-known path rather than go in a new, different direction. So in some sense, I believe we should be less conservative in the way we approach the problems of climate science, and we define the problems of climate science.
So it seems like what you say, the technology defines, like whoever possesses the technology right now has a priority in choosing the methods to test on them, right? What we saw in the past 3-4 months, and was already a tendency that started before, was to give access to these technology big resources. We're talking about clusters of computing, this type of tools, open source tools, in more people with a research background or not, but there has been a democratization of this. At least for a short time, we saw that a lot of resources were available, for example, for the COVID case, and were made available in a very short time. So this, I see this is a tendency that there is no reason for it to stop.
No.
Right?
Climate has been pioneering, as an example, the sharing the data. Okay, so this is something already 15 years ago or more, actually even more, climate scientists have generously shared data. And in the sense of sharing the output of climate models, allowing everyone to look at them and to process them and to do research on them. Let's put it this way. Say you dedicate, you as a person or you as an institution, dedicate an enormous amount of time to the development of a very, very complex model, whose development is a huge and very commendable, very positive effort between technology and science. Now, sometimes this effort takes up all the time and all the resources, or a lot of the time, a lot of the resources that would otherwise be devoted to thinking about and asking scientific questions that such a tool would be extremely helpful to address. That's what I mean. So that the focus, whereas you should have a focus on developing a tool and the focus on answering questions with this tool, since these tools are extremely complex, expensive, and require continuous update, the effort is mostly in the development rather than in the use. Okay? Yeah. So sometimes people run incredibly complex models and all they look at are averages. We know so there is a huge disproportion between the complexity of the process leading to producing these models and the relatively low level of complexity in looking at the data. Somehow you are exhausted with creating and producing this data that you don't have anymore the energy to treat them with sophisticated tools. So that's a problem. That's a problem I see on the sharing of the data and the model. I mean, as I said, climate scientists have been at the forefront, I believe, on this. And I think this is one of the things that attracted me, the ability, the existence of an international coordinated effort to address climate problem. I think it's been, for me, and probably for many others, a huge motivation to join this endeavor.
That's actually true. So there is an optimistic view for the future, like how we're going to use the resources. The more we communicate the new methods, there is a possibility that we're going to shift in methods. We're not going to use the same, and right, it's gonna work this way. And I'm saying it from my own self. Like I see the generation of today, how much more familiar they are with computers and different, using tools of all type, which was a very rare thing if you go 20 years ago, who was able to use computers, and how that maybe this basic literacy in computer will help us elevate and leverage on other things, which is, as you say, the methods, the more complex theory behind it. So I want to thank you, Valerio, for being with us today. And we are open any other time that you would like to talk to us.
Yes,
new research, new topics, or any other thing that.
Okay. Thank you very much.
Thank you very much.